Good morning, everyone, and thank you for joining us on our second of multiple lessons on topics around AP Chemistry. We appreciate you taking the time away from TikTok and Fortnite and joining us here for the next 45 minutes. I am Mr. Sean Byrne. I teach at Glenbard West High School outside of Chicago in Glenelg, Illinois. Go Hilltoppers. And I'm really excited to be here with you to share what will be the second in a long series of lessons. If you haven't had a chance to go back and look at yesterday's lesson about topic 8.1, now might be a great time to stop and go back and watch that lesson to prepare you for what's happening today. Before we get started, I do want to remind you of lots of resources that are going to be continually available for you over the next couple of days and weeks. Anytime you have a question about what's happening in your AP course, we encourage you to go to apcentral.collegeboard.org. When you get there, you will see that there is a link for all of the things that we are doing to support you during your times at home in reaction to the coronavirus precautions. Once you get to this screen, you'll be able to scroll through multiple different resources that are at your disposal. This is just one of many resources that are here to help you make sure that you're prepared for your AP exam in a couple of weeks. Just as a quick reminder that for all of us, our traditional face-to-face exams will not take place. All students will take a 45-minute online free response exam. Many students will take this at home, and some of you will take it at school with your teachers, depending on how your school is reacting to the coronavirus. Stay on there for a minute. Students will be given the choice of two different AP times, two different dates. One of them will be sooner. If you feel like you would like to take it right away while the content is still fresh, that's great. If you want some more time to practice, you'll be given that option as well. And again, your teacher will work that through with you. And so you should continue to communicate with your teacher about the testing dates. All of this information and lots more details will be released on April 3rd, which is a week from tomorrow. So until then, we're going to continue learning chemistry to the best of our ability. And when we have some more information about our exam in particular, everybody will share it with you, especially on apcentral.collegeboard.org. For our class specifically, chemistry, we know that units 1 through 7 will be on the exam, and units 8 and 9 will not be on the exam. You might notice that today's lesson and yesterday's and tomorrow cover topics that are important from unit 8. This is because we feel that these is still very important information for you to know about chemistry, and because colleges has asked us to continue to work with you on these important topics. Eventually, many of you will go on to other science classes, maybe even more chemistry, and we know that this is important information for you to use when you get to those courses. There are multiple classes, multiple review sessions that are going to be happening every day for your pleasure. If you, right here, we're at chemistry, period 2. I myself will be tuning in for my good friend, Kristen Brandt, when she'll be teaching us about some human geography later this afternoon. So let's get into our lesson overview. Today, as I said, we will be focusing in on topic 8.2, which is on the pH and pOH of strong acids and strong bases. This will build heavily on the material from yesterday, which was looking at the pH and the pOH of water in particular. So again, I would encourage you to stop when you have a minute and go back to watch that video. We will be looking at many of the mathematical routines and how to solve mathematical problems on pH and pOH. Yesterday's topic alluded multiple times to Bronsted-Lowry acids and bases and conjugate acid bases and pairs. Conjugate acid-base pairs, excuse me. We'll do the same thing today, and we will spend a lot of time looking at models and representations of how molecules work when they are in an aqueous solution. Next, we're going to make sure that we are feeling very good about drawing reactions, writing reactions, balancing those reactions so that they are consistent with a particulate model. Again, our particle pictures will be very important today. Stoichiometry never leaves the conversation when we're talking about chemistry, and so we'll have some simple stoichiometry problems today, but we're again laying the foundation for what you will do tomorrow. So make sure that these mathematical routines are good habits for you starting today so that you'll be able to take them out for a ride tomorrow when the math gets a little bit more challenging. I've put together a number of different pictures for you, like I said, and then we can't talk about pH without talking about solutions and how the molarity of the solution is going to change our understanding of what's happening with the pH. So this is lots of mathematical routines, as I think you can see we're going to be working with today. The overview, the plan that I have for today is we'll do a quick review of the problems that Mr. Faribaugh gave you yesterday and the topics that he covered in terms of pH, pOH, and kW. And then by the end of today's class, you should feel really comfortable finding the hydronium ion concentration, the pH, the hydroxide ion concentration, and the pOH of a strong acid and a strong base. We'll give you multiple opportunities to do that directly. And then we'll give you a couple of AP problems or AP-like problems to be able to take your skills to the next level. So our warm-up every day is going to be in response to the problems that you saw yesterday. So the first problem that Mr. Faribaugh gave us asked us to consider what happens with hydrogen iodide. And we have a solution of hydrogen iodide that gets added to a solution of methylamine, CH3NH2. The problem tells us that this is an acid-base reaction and that then all of the water is removed by evaporation to produce crystals of the ionic compound methylammonium iodide. Here again, we see the idea of a conjugate acid-base pair is coming up again for us to consider. So think about how methylamine and methylammonium behave as a conjugate acid-base pair based on what you remember from tomorrow. Our question for today, or to begin with, is does the methylamine behave as an acid or a base in this reaction? And I think one of the keys here, one of the tricks, is to look at hydrogen iodide in an aqueous solution. And I hope that that jumps out at you as one of our 7 strong acids. Especially when it's in an aqueous environment, hydrogen iodide can be called hydroiodic acid and is one of the 7 strong acids that we have listed up here. This is a great piece of information to put on a note card for yourself to review on a daily basis between now and your exam date. The more you're familiar with these, the more automatic these strong acids are for you, the easier problems are going to be for you to solve because you won't have to think as much about this. So that sort of hints at what the answer to this question is going to be, but let's dive even deeper. I'm going to isolate what are the important chemicals that are a part of the problem that's given to us. I tell my students regularly that we have to start chemistry by writing some sort of a reaction. So based on the information that's given to us in this paragraph, we see that HI is reacting with CH3 and H2 to make methyl ammonium iodide. Now at this point, you may still not be able to write the formula for this, but I promise in a couple minutes, this will jump off the page at you. So if we have identified that hydrogen iodide or hydroiodic acid is behaving as an acid, then we can assume that methylamine is behaving as a base in this reaction. Now, however, we want to make sure that we're using good chemistry to answer this question. So saying that hydroiodic acid is an acid, so the other one must be a base, is probably not the strongest answer for us to provide here. And we would want to go back to good chemical principles that say that methylamine behaves as a base because it accepts a proton. Bases, by definition, are proton acceptors. And that would be a really nice final answer here. For those of you that are having a hard time seeing how methylamine can be a proton acceptor, let's look at some pictures of some different representations of what this could look like. So one way to talk about this reaction would be to draw some particle pictures. Hydrogen iodide might be represented something like this, with our hydrogen being the white sphere here and iodide being a purple one. Methylamine would look something like this, where we have a methyl group, C carbon with 3 H's around the outside of it, bonded to an amine group. Now, what I hope jumps out at you is the fact that this has a lone pair of electrons that is hanging off the right side of this. This is an area where methylamine can accept a proton because this lone pair is ripe for accepting that proton. Our next, the solution or the products of this would be something like iodide, a nice negatively charged particle, having lost that hydrogen, and methylamine turning into methyl ammonium as it has a positive one charge. The proton that was here joins on to the amine group over here, and we have our carbon with 3 hydrogens around it, our nitrogen with 3 hydrogens around it as well. A third way we might represent this reaction would be to look at Lewis structures. So you may feel comfortable writing HI. The iodine has lone pairs around the outside here, but if this is acting as an acid, this hydrogen is going to be able to jump out. We see a lone pair on nitrogen hanging out over here again. This gives us our iodide ion on the right and our methyl ammonium in the middle. It's important for us to note that the hydrogen is bonded to the nitrogen here. It is not bonded to the carbon. Our carbon is stable with its 4 bonds around it. Adding a 5th one in there would be very destabilizing and not the expected way that the hydrogen would join itself over here. And so this structure over here is probably the best way for us to consider methyl ammonium. And that hints at this answer to the second part of this problem, right? The second part of the problem asked us to write the chemical formula, including the correct charge for the methyl ammonium ion. And I hope that based on our earlier pictures, you can see that CH3 NH3 plus 1 is the best way for us to write the formula for methyl ammonium ion. Of course, there's some other ways that you might have gotten to this answer. If you're feeling comfortable with your functional groups and saying that methyl is here and ammonium hints at an NH3 plus, similar to the NH4 ammonium polyatomic ion, that's great. But if looking at thinking about this in terms of particle pictures is a better way for you to do it, then you should go ahead and do that and feel comfortable drawing that on your pages as you're answering these questions. The second problem that we were asked to consider from yesterday, again, looks at hydrogen iodide, but looks at the relationship between the temperature of this reaction and the equilibrium constant. We're asked to consider, is the forward reaction, as written, an endothermic process or an exothermic process, and to justify our answer. So the first thing that I noticed when I looked at this was that as the temperature increased, our equilibrium constant decreased. We see that the temperature goes from 298 to 700, an increase, but the equilibrium constant decreases from 790 to 55. Because the equilibrium constant is written as products over reactants, this hints at the idea that when the temperature goes up, we have fewer products relative to reactants in our second experiment here. So I think a good response to this would say that the equilibrium constant K decreases when the temperature increases. We're stating what piece of information, what piece of evidence we're pulling out from this data. And this indicates that the amount of products at equilibrium is less at higher temperatures. Raising the temperature shifts the equilibrium to the left, meaning that we are using up some energy or towards the endothermic reaction. And this indicates that as written, the equation is exothermic, that energy can be considered some sort of a product here. And when the temperature goes up, we're going to use up that product to shift it to the left. Okay, so let's jump into our lessons on pH and what you need to know for today. Like I said, we're going to start with a quick review of what we did yesterday and a review of pH, pOH, and kW. If you feel like you would like to stop at this point again and go back to watch our lesson from yesterday, this would be a great time to do this. This entire lesson will be recorded and you can come back to this at any time that you would like. We know that all of pH is built on the foundation of the auto-ionization of water, that all of the principles that we're looking at over the course of the next couple of days come back to this reaction of water reacting with itself to make hydronium ions and hydroxide ions. We know that at 25 degrees Celsius, experimental results tell us that the Kw, or the product of hydronium ions and hydroxide ions, is 1.0 times 10 to the minus 14th. What we'll use today is two different variations of this equation that you would want to be comfortable with. While this information on the center of the screen is available to you on the AP Chemistry equations page, the rearrangement of both of these equations into the equation to the bottom is not given to you per se. And this is just algebra. We're dividing the OH to one side or the hydronium ions to the other side. If we are given an OH concentration and we want to find the hydronium, we would use an equation that looks like this. If we're given the hydronium and we're trying to find the OHs, we would use an equation like this. I just used algebra to get here, and you will always have this equation at your disposal. So let's consider a question where we are given a hydrochloric acid solution that's at 0.0025 molar, and we're asked to find the pH and the pOH. Like we said before, we're going to start every equation or every problem by trying to write a reaction. So hydrochloric acid is reacting with water to make hydronium ions and chloride ions. If we are told that we have a 0.0025 molar concentration or solution of hydrochloric acid, we can assume that we have a 0.0025 molar concentration of hydronium ions. Now, I'm going to give you a second to think about why we are okay making that assumption. And I hope that many of you remembered that hydrochloric acid is a strong acid. It's one of our 7 that we need to continue to come back to. So if hydrochloric acid is a strong acid, which it is, we know that it completely dissociates when it's put into water. This is why I can write an arrow here instead of an equilibrium symbol, and why I can assume that hydrochloric acid, the concentration of hydrochloric acid is the same as the concentration of the hydronium ions here. So the first step of this is solved for us pretty easily just by using our chemistry knowledge and no math at all. I promise you tomorrow, that first step will get a little bit trickier. So making sure that we're comfortable with it today is probably a great idea. To get to our hydroxide ion concentration, we're going to use this equation from the previous slide. We're looking at Kw divided by the hydronium ion concentration, 1.0 times 10 to the minus 14th divided by 0.0025. And that solution is 4.0 times 10 to the minus 12th. Now, in a minute, I'm going to solve one of these problems live with you and show you how we would put this into our calculator. So if I'm going a little bit fast right now, be patient with me, and I'll show you how this would look on a calculator. Next, we can get to the meat of the problem and answer the question as it's given to us, where we say the pH is equal to the negative log of the hydronium ion concentration. So pH is equal to the negative log of 0.0025, and that is 2.60. Similarly, our pOH is equal to the negative log of OH, which is the same as negative log of 4.0 times 10 to the minus 12th, and our solution there is 11.4. Now, many of you may see a simpler or an easier way to get through any of the 4 problems, any of the 4 answers that are here. You may recognize that pH plus pOH is going to consistently add up to 14. And that's great. You probably are very familiar with your log properties. You remember that your Kw, if we take the log of both sides, how that would look. You may be in pre-calculus or beyond, and that's great. If not, the method that I just showed you is going to work all the time. And so you should feel comfortable practicing this way of solving a problem like this. Now let's look at a second problem where instead of looking at an acid, we're looking at a strong base. And NaOH is a great example of a strong base. Our reaction will look something like this, where sodium hydroxide splits apart into sodium ions and hydroxides. And because sodium hydroxide is a strong base, we can say that our concentration of NaOH is equal to our concentration of hydroxide ions. And so for this problem, we're going to start on the right side of my table here at the bottom, the right side of my page, say that the OH concentration is equal to 0.0015 molar. Similar, but slightly different from what we did earlier, our concentration of hydroniums is 1.0 times 10 to the minus 14th divided by that hydroxide ion concentration. And so that's equal to 0.0015, giving us a hydronium ion concentration of 6.7 times 10 to the minus 12th. We're almost there. We're going to look at our pH to give us our final answer. Our pH is equal to the negative log of our hydroniums, which is equal to 11.18. And our pOH is equal to 2.82. And a really good spot check for myself is to add these two up and say, do they equal 14? They do, and so I know that I'm on the right track. So let's do some practice together now. We're going to mix things up a little bit. And if you are watching from wherever you are and your name begins with A through F, I'm going to encourage you to look at that first problem. If your name begins with G through M, I'm going to encourage you to look at that second one with KOH. If your name begins with N through T, look at that third problem with HNO3. I'll give you a warning there that nitric acid is a strong acid, and so you can use the same methods that we've used in the past. Lastly, if your name begins with U through Z, why don't you analyze lithium hydroxide there for us and see what you can come up with. I'm going to give you approximately 30 seconds to get started on these problems. I'm going to switch over to my iPad so that I can solve it live for you. If you feel like you would like to pause the video and solve this entire thing out, I'm going to give you solutions to all 4 of these problems, which means that you have 4 practice problems that you can come back to later on today or over the next couple of weeks as you are going on and practicing for the exam. So go ahead and jump into one of these on a scratch piece of paper, in a notebook, on an iPad, or wherever you are able to. I'm going to switch my technology for a minute and I'll be back to you in about 20 seconds. I'll give you about 10 more seconds to continue your work, and then I'm going to begin with the problem that's shown on the screen. So being at the beginning of the alphabet, I know that we tend to get our problem solved first. So I'm going to jump to our last problem that I shared with you for the end of the alphabet and let you guys see this problem solved live. As I said, I'm going to show you a solution to all 4 of the problems back on our screen in a couple of minutes. But if we wanted to think about how this would be put into the calculator, how we would solve all the steps here, I thought it'd be useful to show how I would write this out. So we're looking at lithium hydroxide, and we're being asked to find the same 4 quantities that we have done before. So I'm going to start by writing an equation. And I'm going to recognize that if I have 8.75 times 10 to the minus 3rd molar concentration of Na or of LiOH, that gives me 8.75 times 10 to the minus 3rd molar concentration of hydroxides. Why? Because we've said that this is a strong base. Great. So then our next step would be to say that our hydroxide ion concentration is equal to 8.75 times 10 to the minus 3rd molar. I'm going to try to be really careful with my units here and make sure that I include units on everywhere where it's appropriate. In this problem, I'm going to jump ahead to the pOH just to show that we can do this in a different order. So the negative log of the hydroxide ion concentration. So our pOH is equal to the negative log of 8.75 times 10 to the minus third. So our pOH is going to be equal to, and if you want to follow along with me on my calculator over here, I have the negative log of 8.75 exponent negative 3, and I get 2.60 as my answer. That's wrong, 2.06, excuse me. Keep me honest, thank you. My hydronium ion concentration is going to be equal to Kw divided by my hydroxide ion concentration. So for this equation, I have 1.0 times 10 to the minus 14 divided by 8.75 times 10 to the minus third. So 1.0 E minus 14 divided by 8.75 E minus 3. And I have an answer that is, just double checking my work over here, H30 plus is equal to 1.14 times 10 to the minus 12th. Are you still with me? pH at this point is equal to my negative log of my H30 plus. pH is equal to the negative log of 1.14 times 10 to the minus 12th. So my pH is equal to the negative log of 1.14 E minus 12. And I get 1.19 times 10 to the 1, which is 11.9. And when I did this on a different calculator, I got another decimal point there and I got 11.94. So go ahead and check that at home to make sure that I did that correctly. But my spot check is to see if these two numbers add up to 14. And because they do add up to 14, I know that I'm on the right track. So excuse my messy handwriting there, but I did want to just show you kind of the thought process through solving each of these problems, as well as how this might look in a calculator, because I know that some of my students do have a hard time with the calculator aspect of this, and so we will. I just wanted to show that to you. Hold on for just a second, and I'm going to stop sharing this screen. And we'll go back to sharing this screen. Okay. So 4 different problems for you to look at here. As I said earlier, you can feel comfortable to go back to any of these 4 problems at any time. And the solutions should be here for the first problem, A through F. So if you were working along with us, check your work. If you were solving problem G through M, sorry, if your name begins with G through M and you were doing our second problem, that is, on KOH, here's your solutions. If your name begins with N through T, excuse me, here are your solutions. And lastly, I hope that these numbers match with what we had earlier, and I'm pretty sure that they do, so we're good. So you can feel free to take screenshots of these or bookmark this and come back to it as some really nice guided practice problems. Like I said, these are pretty straightforward in terms of the math and the chemistry. Tomorrow we will be kicking it up a notch, but you want to feel really comfortable on these problems so that when we do get a little bit more challenging, we have the same skills kind of developed in our brains. A second problem that is coming right out of an AP-like kind of problem, where we're asked to analyze 3 different solutions. The first one is 100 milliliters of 0.1 molar HCl. The second one is 200 milliliters of a 0.5 molar NaOH solution. And the third beaker has just 300 milliliters of distilled water. And we'd like you to rank these solutions in order of increasing pH, and then consider which of them would have the greatest change in pH by the addition of 100 milliliters of distilled water. So I'm going to give you about 30 seconds just to start setting up that first problem to see What information jumps off the page at you? And are you able to rank these solutions? About 5 more seconds just to write down a quick thought or a idea about how you would tackle this problem. Okay, great. If you need more time, feel free to pause and come back to us when we have when you have a good solution that you want to compare to our solution. So I would set up some sort of a table that looks like this. And I would want to make sure that I analyze each solution independently before I try to compare them. So for solution X, hydrochloric acid, we have hydrochloric acid as a strong base. Ding, ding, ding. We remember that from earlier, is reacting with water to make our hydroniums and our chlorides. I'm sorry if the picture is cut off up there, but underneath the picture, you should see chloride Cl minus. That means that the pH is equal to the negative log of our 0.01 because hydrochloric acid is equal to, because it's a strong acid, right? So HCl is will completely dissociate. So the concentration of HCl's is the same as the concentration of hydroniums. And so our negative log of 0.1 is equal to 1. Similarly, our NaOH will split apart or dissociate like this. So our pOH is our negative log of 0.5. And if we put that into a calculator, we would see that that's equal to 0.3. Now there's a trick here that this problem is asking us to put the solutions in order of increasing pH, not pOH. And so we need to take the added step here of saying that the pH is equal to 14 minus the pOH, and that would give us 13.7. Lastly, our water is just distilled water. And because the problem told us that we're at 25 degrees Celsius, go back and read that carefully. We know from yesterday that our pH of a water solution is equal to 25 degrees Celsius. Now you may notice in this that I did not take the volumes of the solutions into account at all, that this was only, I only looked at the concentrations. And that's because we know pH is only reliant or only dependent on the concentrations of the solutions. It's not reliant on the volumes of the solutions. And so the fact that this is a larger volume has no impact on the pH. You may understand that this is going to have an impact on what happens in the second part of that problem, but for this step right here, we're just fine. So our final step is to make sure that we have answered the question. The question asks us to rank the solutions in increasing order of pH. So we're going to start with the lowest, which is 1. Then we would go to solution Z, which is water at 7. And we'd end up with solution Y, which is our basic solution. Now, many of you may have looked at this and been able to say, oh, this is acid, it has a low pH. This is base, so it has a high pH, and water should be somewhere in the middle. And so you'd be able to rank it like this. And that's great. If that doesn't immediately jump off the page at you, this is a great way to make sure that you have some mathematical data to back up what your correct reasoning is at this point. The second problem asks us to consider which of the 3 solution will have the greatest change in pH by the addition of 100 liters of water. And in this case, we need to justify our answer. So take another 30 seconds to consider how you would even set this up, what kind of pictures you might draw, and I'll be back with you in 15 or 20 seconds now. So for me, I would set up a problem or a table that looks something like this, where I want to analyze the original solution to the new solution. And by new solution, I mean the addition of another 100 milliliters of distilled water. So if my original solution was 100 milliliters, my new solution is 200 milliliters. And if my original concentration was 0.1 molar, I know that my new solution is 0.05 molar. How did I get that? Well, when the volume doubles, the concentration would be cut in half, especially if I'm just adding water. Many of us can do that problem in our head, but if you can't do that in your head, I'm going to show you in just a second of how you could mathematically prove that relationship. Using the same equation that we've used multiple times today, the pH of a 0.05 molar hydrochloric acid solution would be 1.3. For solution Y, we go from 200 milliliters. Oh, excuse me. The change in pH here, there we go, is going to be 0.3. We went from 1.0 to 1.3, and so our difference, or our change here, is 0.3. Solution Y started at 200 milliliters and it's going to go to 300 milliliters. And so solving for the molarity here is probably much more challenging for many of us. And so we'll do a quick dilutions review here. Remember that the equation for a dilution is dependent on the fact that the number of moles of solute do not change. So we can say M1 times V1 is equal to M2 times V2. This equation is given to you on the equation page, and so it's not something you need to memorize, but it is a really handy one to use in multiple instances. If we are solving for M2, so the molarity of our new solution would be an M2, we can say M1 times V1 divided by V2. I will plug in my numbers here, and I would get a final molarity of 0.33. Now, many students will take the added step of converting the volumes here to liters. And typically we would look at volumes in liters. So we would have 0.2 and 0.3. But because the relationship between the volumes 2 to 3 or 0.2 to 0.3 stays the same, we can plug these numbers in to still get the same answer. So our new molarity here is 0.33 molar NaOH, and that's kind of the key to this problem. So our pH goes from 13.7 to 13.52 for a difference of 0.17. This pH happens to be going down, but the overall difference is 0.17. Water doesn't change, right? We add some more water to it, but the pH is not going to change. As we learned yesterday, the only way we're going to change the pH of distilled water is to change the temperature. So as long as we stayed at 25 degrees Celsius, which the problem told us, we have no change in our pH. So a good solution to this would be to clearly identify that solution X will have the largest change in pH after 100 milliliters of water is added, because the concentration of the solution is changed the most. The larger change in concentration will cause a larger change in pH. This problem asked us to give a solution and to give an explanation. And so I think both of these sentences are important for you to include on your final answer so that the reader understands that you had more than just a lucky guess, that you really thought through what the answer was and you have good reasoning behind what your answer is. And that brings us to the end of our official lesson for today. As we went through all of our material today, we reviewed our pH, our pOH, and our kW from yesterday. I hope you're feeling much more confident on finding those 4 quantities for a strong base and for a strong acid. If not, you can watch this video multiple times because it is being recorded and will be available to you within the next couple of minutes. Our exam practice problems for tomorrow, we have 2 of them for you. If you want to take a screenshot of this, or you want to pause the video right here so that you can write down the important information. This one comes from the 2014 AP Chemistry exam. It looks very similar to, it is the same beginning prompt from what we looked at yesterday, but we're looking at part C2. Part C asks us to determine if this statement is true or false. We're looking at the pH of hydrochloric acid is the same as the pH of the propanoic acid. And the propanoic acid is identified up here as a pH of 2.79. So you probably are not yet able to determine the pH, the concentration of the propanoic acid, but given the fact that hydrochloric acid has a pH of 2.79, you should have enough information now to solve for the molar concentration of hydrochloric acid. So we would like you to calculate that before tomorrow's lesson. And then what Mr. Faribault will do was help you to solve that and preview what we would do for propanoic acid. And by the end of class tomorrow, you would be able to solve all of this problem. Second problem for you is to consider 4 different acids, 1, 2, 3, and 4. This may be cut off, but it says pH of acid 4 up here. And each of these acids was tested at 5 different concentrations. These are increasing concentrations, and the pH of each of them was measured. The experimenter knows that these 4 acids are chloric, lactic, and propanoic acid, but we don't know which one is which. But you should have enough information to be able to determine which of the 4 acids listed in the table is hydrochloric acid. So think about the knowledge that you have so far, and you will be able to answer this question. Again, Mr. Faribault will answer this question for you at the beginning of class tomorrow. So thank you so much for sticking with us and for all your efforts on today's problems. As you're working through the next couple of days and weeks, I just want to do a quick reminder again for you to go back to apcentral.collegeboard.org with any questions that you have. I know that information is changing quickly every day, and we will continue to update this page as often as information is available. And so just keep going back to that as often as you can. Another important piece of information is that we know that not all students have consistent access to internet or a device at home. And our plan is to have every student take their AP exams on through the internet on a device. And we really want to make sure that every student has the ability to show their best work. So if you need a tool or you need help with connectivity, or you know somebody who does not have either of these 2 things consistently, please go to cb.org/tech and fill out the form to give us some information about how we can help you. It's really important for us that you show us your best work, and that will allow us to give you the support that you need. So thanks again for watching. I had a great time sharing this information with you. I encourage you to watch this again and to come back and see us again tomorrow. So have a great day.